Hey everyone, my name is Max Itson, and along with Katie Krupczak, Liam Manel, Mark Wellman, and Nathan Farmer, we have developed an Alzheimer's prediction model for our semester project. So, what is Alzheimer's? Alzheimer's is a progressive neurodegenerative disorder characterized by the gradual loss of cognitive functions such as memory and reasoning skills. It is characterized by the accumulation of amyloid beta plaques and tau tangles in the brain, disrupting cell function and resulting in cell death. The primary way to detect Alzheimer's disease is through the use of MRI scans. These scans are used to assess the volume change caused by cell death in the messiotemporal lobe and the temporoparietal cortex. Through the use of image recognition, we believe it is possible to use machine learning to detect whether a person has Alzheimer's or not and to what severity they have it. With the scans below, we can visually see the difference between the stages of dementia, primarily around the center of the brain. The non-demented patient has a strong center with all its neurons still intact. But as we progress down the line, we begin to see these neurons fade out. Although we have MRI scans of different types, we will mainly be focusing on the results from the non-demented and very mildly demented scans, as we are focusing on the early detection of the disease. Our goal for this semester is to create 3 different machine learning models that can detect Alzheimer's and its severity. We will be using supervised learning for our predictions. For our first model, we implemented a ResNet, but before we get there, we must look at the pre-processing steps. We started with a z-score normalization, as the MRI scans came with different brightnesses. We then performed random horizontal and vertical rotations to combat overfitting. And lastly, we used principal component analysis to reduce our features. Here is a nice visual of our PCA. We wanted to make sure we retained enough variance for our model, but also reduce the number of features. We noticed that at around 30 components, we were able to retain 99.5% of the variance. So for our model, we were able to reduce each image from around 16,384 features to only 900. So now on to the ResNet. ResNet is Microsoft's 34-layer residual neural network pre-trained on 100,000 images of over 200 different classes. It uses deeply layered convolutional neural networks with connections that bypass certain layers, allowing gradients to flow through the network while avoiding vanishing gradients. For this, we used Hugging Face's Transformers API to access both the data, model, and tools to construct the model's metrics. The training data was pre-split into training and testing sets and an 80-20 split. We further split the training data 90-10 into training set and evaluation set. Using the pre-trained ResNet 34, we trained on 3 alterations of the data: plain data with rotations, and the PCA compressed data with rotations. We were able to obtain 3 different accuracies for our ResNet model, each utilizing a different pre-processing method. The first accuracy represents utilizing the plain data, which obtained 96% accuracy, but took forever to run as we are utilizing so many features. The second was an attempt to combat overfitting by utilizing random transformations, but that only ended up at around 86%. The final method was utilizing all the techniques, including PCA, which reduced our image size by 77%, which greatly improved our model's runtime and still produced a very good accuracy at 90%. For our second model, we decided to implement a support vector machine. This model creates a hyperplane in a multidimensional space to separate the data to its different classes. It then predicts incoming data by placing it on the map and figuring out which class it maps to. We decided to try a new pre-processing method as well, consisting of cropping and singular value decomposition. We noticed that the MRI scans vary between the different classes near the center of the brain, so we cropped our images to focus on this region to help reduce the number of features. We then implemented SVD to reduce the amount of noise in our images. As you can see in the bottom right, our images are smaller, but we can still see the difference between the images as the number of neurons varies between the different classes. This model produced really good results, with a model accuracy of 96.7%. We're trying to find Alzheimer's early in the process before it gets too deep, so we really like to focus on the non-demented and very mildly demented and see how we did there. Both of those have really good recall, precision, and F1 scores, so we're very happy about how this model performed. For our last model, we decided to implement K-nearest neighbors. This is a machine learning algorithm that classifies new data points based on the majority class of its K closest neighbors in the training set. We chose this because it is known for being quite easy to set up and quickly tune if the dataset is small enough and does not have too many features. Therefore, this algorithm would be a great fit for our problem, as the pre-processing technique used in our second model's implementation significantly reduced the data's feature space while maintaining the vast majority of relevant information. To implement the algorithm with our data, we first pre-processed the data in identical manner to what we did with SVM, and then utilized sklearn's k-nearest classifier and tested both changes in the number of neighbors and the method for the weighting neighbors. In the end, we determined the most effective parameters by experimenting with the algorithm using between 1 and 15 neighbors, and with either a uniform or distance-based weighting evaluator. The model greatly depends on its k-value, as small values can be swayed by noise, while larger values will be persuaded incoming data to match with the class of greatest size. This model is easily the most surprising of the bunch, because we found the best results with a k-value equal to 1. As k increased, our overall accuracy strictly decreased. We believe this is to be because our dataset is so small, but nevertheless, we were still able to get a 98% overall accuracy. It's funny to think that the model that is the simplest of the bunch performed the best overall. In conclusion, all three models demonstrated promising results in identifying and classifying the early stages of Alzheimer's disease. Based on the evaluation metrics we defined for our problem, the KNN algorithm seemed to perform the best, having the highest overall accuracy of 98%, while also maintaining really good recall values for classifying the more demented MRI scans. Using these models, it is possible to both identify patients in the early stages of dementia and classify the severity of their illness. These findings also underscore the potential for machine learning in enhancing early detection and accurate diagnosis of the disease. Early detection is crucial, as it allows for timely intervention and potentially slowing the progression of the disease and improving patient quality for life. However, these results do come with some cautionary notes, one of which being that our dataset is so small. It is very possible our models are overfitted to this dataset, and it will be able to generalize to other MRI scans. Another note is that although our training and test set contains fewer examples of moderate dementia, the use case for these models is focused on early diagnosis before overt symptoms appear. There are some ways that we can take this project further, the number one being to acquire more data. It is possible that our models have been overfitted to our dataset, and the only way to solidify or disprove that claim is to acquire more data. The second is to find different image recognition algorithms to focus on the specific areas of the brain known to be early targets of the Alzheimer's disease. We noticed trends in the MRI scans toward the center of the brain, so we cropped our images to focus there. But there could be other areas of the brain that could be easier and could also be more accurate. Lastly, we would like to investigate other pre-trained models like the VGG16 instead of the simpler models that we used in Microsoft's ResNet. Overall, we are very happy with the performance of the project, and we look forward to see what it can do in the future.